I've wanted to make sure that kids in our community have had the best opportunity to stay connected with their learning, particularly in science while they've been at home. So I teamed up with one of Australia's leading scientists, Professor Alan Duffy of Swinburne University. He's an astrophysicist and he's also the lead scientist at Australia's Science Channel. And he's here to answer your questions about space and science, and we've picked a few of them to show you today. Take it away, Professor Duffy.
Thank you so much for these questions. Melissa, you have some incredibly smart and engaged and enthusiastic young minds in your electorate.
Lindsay asks, what is the ozone layer made of?
This first question I love. Lindsay, yes, what is the ozone layer made of? Well, the name implies it is ozone. Ozone is 3 oxygen atoms that are stuck together. The air that we breathe, the oxygen we breathe, that's where you get 2 of them stuck together. And this special type of oxygen sits very far above our heads, very high in the atmosphere above us, and it acts as a block. It gets in the way of harmful radiation from the sun that we call ultraviolet, and that's a very dangerous type of light, and we want to and that's why we use sunscreen, right? Slip, slop, slap, you put on sunscreen to protect yourself from ultraviolet. Well, it would be even worse if we didn't have the ozone layer, because it's actually absorbing that ultraviolet radiation, and it's doing that, essentially it breaks apart. The molecule, the ozone, breaks apart into the oxygen atoms in absorbing that ultraviolet, getting in the way of that harmful radiation and protecting us here on Earth. But the ozone layer as a name is not, it's not quite, it's a little misleading, and that's because the layer is, if anything, too generous. The ozone, if you were to squish all the ozone, it's very, very dispersed throughout all of the atmosphere. If you were to squish it all together, it would be 3 millimeters thick, about the thickness of a coin. You do the same to the atmosphere, you stick it all together, it would be something like 8 kilometers of air, and then a little layer just 3 millimeters thick on top, and that's the protective ozone layer. So it's something very fragile, and we should all be very thankful that it's there.
Lindsay asks, why do compasses point to the north instead of the south?
This question about compasses is brilliant. So why do compasses point to the north instead of the south? Well, that's because the compasses are just little magnets, and they're able to turn around and float around, and they want to line up and they want to point in a certain direction, and that's the magnetic field of the Earth. Now, if you remember, if you have 2 little magnets, we always say that opposites attract. So if you get the 2 north ends, they'll repel, they'll push away from each other. But if you have the north and the south end, they'll come together, they'll actually point together. So when we have a compass and it's pointing towards the North Pole, towards the direction of the North Pole, and we say that's the, magnetic north is up that way, well, opposites attract. So actually the bit of the compass that's pointing towards north is actually the South Pole bit of our little compass, which is itself a little magnet. So then we just draw a little N on the end of that, or we paint it red, or do whatever to indicate that little side of our compass that's pointing up towards the North Pole, and we just draw a little N on that. And that reminds us it's actually northward pointing, but technically that's the South Pole end of that little compass magnet that points towards north. Now, we have these compasses, these magnetic poles are always moving, and they can flip. And so sometimes in our history, the North Magnetic Pole, not the North Pole where Santa lives and the Earth spins around, but the magnetic pole, so that can actually move and it can flip. So the North Pole flips and turns south. So our compasses would actually then point south. So what would we do about that? Well, we would probably just rename our compasses. And in fact, that movement, that flip is happening right now. the South Pole has actually, the magnetic South Pole has left Antarctica. It's actually on its way towards our direction, if anything. It may take hundreds or even thousands of years to fully flip, north and south to flip, but it's happening right now.
Dylan asks, how was our solar system made and what was the first planet?
Melissa, I love this question from Dylan. How do the planets form? Well, they all start off as a giant cloud of gas. Those are atoms that make up our body, that make up the stars and everything else that we can see. So there's a giant cloud of gas, and then its gravity begins to pull together, just like things fall towards the Earth. Now, this whole object, giant, enormous cloud of gas, billions and billions of years ago, before the sun itself had even formed, all of that came together, began to collapse, and just as a ice skater, if they're spinning around, and they bring their hands together and they spin faster in the same way as that gas cloud began to get ever more dense, smaller and smaller and smaller under its own gravity, it also began to speed up its rotation. In the middle, it got dense enough that finally a star was born. That's our sun. And then all around this newly formed sun was a disk, like a pancake of material, of these atoms that were clumping together, growing bigger into grains of sand that collided. All of this is happening over the course of millions of years. Finally, these clumps get big enough that we call them protoplanets, and eventually even entire planets that we see around us. But the key is they're all still spinning in the same direction, which is that same spin that cloud of gas had. And just like the ice skater bringing their arms in, as that cloud shrunk in size, it span up ever faster, and we can now see that in the way all the planets rotate around our sun. What was the first planet formed? I love that you asked the question, because that indicates that you're thinking, well, I don't have to take for granted everything I see. Maybe some of them formed before others, and you're absolutely right. Dylan, the first planet we think that was formed was the planet Jupiter. And within about 1 million years, it was already 20 times the mass of our Earth. It has been, it has helped shape our solar system through its enormous gravity, its enormous size. And in fact, it probably deflects a lot of the asteroids that would otherwise hit our planet. Hoovers them up like a giant vacuum cleaner. So we've got a lot to thank Jupiter for. Not just that we have a solar system that looks like it does today, but also that we, have it shielding us from dinosaur destroying comets and asteroids. Obviously, the one that got the dinosaurs got through, but who knows how many it stopped in the years since.
Dylan asks, how did they discover the planets?
This follow-up question about how do we discover planets is really good. And I wish I could give you a fancier answer, but we just look. It's the same way that that you can do tonight. You can look up into the sky and you can see a type of star that doesn't seem to twinkle. Some of these can be very bright, and these are the planets. So we see planets in our solar system. They're reflecting the sunlight back to our eyes. Because they're within our solar system, they're actually big enough that they don't twinkle like stars, which are very, very distant from us. So when we look out into the night sky, we're looking for basically a bright point of light that's not twinkling. And you can see Venus, which is closer to the sun, or Jupiter, which is often very far away in the night sky. But more than that, as you go for ever more distant planets, they become really quite faint. It becomes very hard, in fact, when you look at the night sky, to tell the difference between what is just a very small or distant planet and just a very faint distant star. So we use another little technique, which is that we watch for those planets that they actually slowly over the course of a year, they'll actually move in the sky against the background stars, which appear essentially fixed in place. So what we're looking for is a little point of light that very slowly moves across the sky. It's very, very precise work, very hard to do. Once we've found a planet, though, we do something very smart. In particular, the planet Uranus. We had its orbit. We knew where it would go. Once we discovered it, we could actually then predict using mathematics where would it be next year and the year after that and the year after that in this movement. And we noticed that it wasn't quite moving in the way we thought. It was almost as if there was another equally huge planet further out whose gravity was pulling on it and actually changing the orbit in a way that we could only explain by the presence of this other planet. So with mathematics, we predicted where is this other planet, and then we turned our telescopes, and sure enough, there it was, a point of light exactly where we thought it should be. It was the planet Neptune. So we discover planets by careful observation and very precise mathematics. And it's the kind of thing you can do from your backyard.
Lucas asks, what is the new planet made of, and are there any special gemstones in its makeup?
So Melissa, you're a lecturer. They're clearly on the very cutting edge of science. I love it. I love this question, Lucas. Thank you for it. We have just discovered a new alien world, Kepler 1649c. It's not very catchy, I know. I think, Duffy's world would be cool. Maybe someone can suggest that to NASA. The way we found this world around this distant star, about 300 light years away, and what that means, it's taken light 300 years to reach us from that star and the planet that's going around it. It also means that were there aliens on that planet looking at us, they'd see the planet Earth as it was 300 years ago, back in the 1720. What was happening then in the world, it would look very different to now. So you're always seeing back in the past as things were when the light left. So with this world, we think it is a rocky planet. It's almost exactly the same size as the Earth, maybe a few hundreds of kilometers wider. This means it's likely to be similar in terms of its rocky composition to us, and that means that we can assume, and it's pretty brave, but we can assume it has gemstones, which was I love as part of your question. These what types of gemstones you get just depends on the types of elements that you have. What is your planet made of? Is it aluminium or different types of sulfur or coppers and all the beautiful elements that go into making these gorgeous different colored gemstones? It entirely depends on the exact makeup of this alien world, and all planets are different. Even in our own solar system, they're all formed from the same cloud of gas at the start. If you look at their compositions, they're all subtly very different. What we don't know about this planet, it appears, I should say, it's at the right distance from its star to have liquid water, just like we do. We call this the habitable zone, or the Goldilocks zone. It's not too close and too hot. It's not too far away and too cold. It's just right. That's the Goldilocks zone for liquid water to exist. But until we can get a closer look and see, does it have an atmosphere, we don't know for sure what its surface is, if it has liquid water, and then the presence of life and everything else. That's super exciting to try to find out. All those questions have to wait for further pictures to be taken, but it's a really exciting discovery. And I love that you're already thinking of what cool gemstones you could get on that surface, on that world. I should point out, for the longest time, we thought that Jupiter would actually have a diamond at its core, that actually this diamond would be the size of the Earth itself. Now, we sort of think that's probably not going to happen now for super complex reasons, but we still don't know. It's still possible. And I just love the idea of a giant diamond the size of the Earth in the center of Jupiter. So these gemstones are right there.
Brandon asks, are infinity stones real, and could they wipe out half the universe?
I love this infinity stone question, Brandon, because, firstly, Are Infinity Stones real? So what are Infinity Stones? I'm a nerd. I love Marvel. I love comic books and superhero films. The Infinity Stones, there's 6 of them. They're all formed at the very start of the universe in the Big Bang, and they all represent a cool power of space or time or anything else. The key is if you bring them all together, then you become all powerful, and you can, as you've asked, wipe out half a universe or every other living creature in the universe. We don't need to worry about that. There's definitely no risk. There is no way the Infinity Stones are real. There are powerful rocks out there, and we call them radioactive rocks, like uranium, which is something that Australia mines a lot of, and with that you can power entire cities and even the world. So there are powerful rocks out there, but they're not quite as powerful as the Infinity Stones. And even if we could see something as powerful as that, we still wouldn't be able to wipe out half the universe. It's a big place. So we're safe and sound. But the key thing from the Avengers Endgame, I don't know how old you are. I think that's an actual, like 13. Anyways, that movie is a little scary, but the key is, and I won't spoil it, but someone who saves the day is a scientist, is an engineer, and it's science and technology that saves us all. So if you want to be a superhero, or at least have superpowers, science and technology, it is a superpower. So make sure you study it. And then maybe you can save us from something in the future, even if it's not an Infinity Stone.
Connor asks, how did the Big Bang happen?
How did the Big Bang happen? Melissa, you're a lecturer. They're really asking easy questions here. Okay, Connor, I don't know. Simple truth. I don't know, and no one knows. We don't know how the Big Bang happened. I'll tell you what we do know. We know that if we look out into the sky, that every galaxy is moving away from every other galaxy. And that means that in the past, they were closer together. And in the earlier, much more distant past, they were even closer together. And in fact, if you wind the clock back 13.6 billion years, that's like over 3 times the age of our solar system, you would get all of the objects lying on top of each other. All of this stuff crushed into a tiny volume, bit of space, would have incredible density, incredible temperature, incredible pressure, energy would be crazy. In other words, it would, if you start with that and you hit play on the video, it's a bang. Very big bang, the biggest of all possible bangs. You wouldn't get a sound because you're already in it, but you know, the Big Bang was everywhere, rather everything was created in that Big Bang, including, we think, time itself. So the issue we face, and all of our physics breaks down at this point, we can't say how it happened or even what came before it, because as far as we know, time itself started at that point, or certainly that's what our theories at present suggest. Now, whether that's true, whether we need just a better theory, I leave to smarter people than I to try to create those new theories, a new Einstein, and maybe that new Einstein is watching this, or maybe going to get inspired. They're going to come out of Western Sydney and change the world with this new theory of what the Big Bang was and how it happened. I wish I could tell you. I'm not smart enough, but I have complete confidence someone watching this is.
Millie asks, what is at the centre of the sun, and how does it stay alight if you need air to create fire?
Millie, what a wonderful question. What is at the centre of the sun, and how does it stay alight if you need air to create fire? Well, I'll answer the second bit first. I'll answer it backwards because you've nailed it. You do need air to create fire. There's no air in space. So that sun isn't burning in the way that a wood log would burn on a fire or gas on a stove. It must be burning in a different way. So it's a giant ball of gas, of atoms, of hydrogen or helium, and that's helium you've come across if you've ever got one of those lighter than air balloons, a party balloon, right? When it's and you get it from a big tank and you squirt the air, the gas into it. So helium is a very light atom. Hydrogen is even lighter, with a big ball of this that is shining bright. That's what we see as the sun. Where's all that energy, that heat coming from that's causing this whole ball of gas to glow bright like a light bulb? Well, we have to go deep inside the sun, and there, as you asked, in the center of the sun, there's just more gas. But something very special is happening, and that's the center is getting squeezed by all of the sun that is around it, crushing it down, incredible densities, pressures, temperatures, just really squeezing the atoms and squeezing them so close together that the hydrogen atoms, they actually fuse. And in doing so, they fuse and they make new, heavier elements, and they release a huge amount of energy. So it's not a fire, it's fusion. It's nuclear fusion, taking small light atoms, squeezing them together to make heavier ones, releasing a huge amount of energy in the process, ultimately forming elements that are in us, like carbon, the carbon, nitrogen, oxygen, for example. In our bodies, the oxygen we breathe, the carbon in our food, carbohydrates, you've heard of that, maybe. All of these things, they were forged inside a star that existed before our solar system, and it exploded outwards and it shed all of that material out of its core, and that got taken up into forming a new solar system. And who knows, at the end of our sun's life, maybe some of the carbon that it's created through fusion will find its way into another solar system and another living creature billions of years in the future. That's the beauty of astronomy. We're part of a journey that has lasted for billions of years and is not going to end anytime soon.
Daniel asks, how does the moon change shape?
Daniel, great question. How does the moon change shape? Okay, well, the moon doesn't change shape, but it does look like it changes shape. Over the course of a month, it goes from completely absent, you can't see it, we call that a new moon, all the way around, increasing in size. It has a little crescent and then gets ever bigger, and then finally a full moon where it's completely illuminated, or it's at its biggest size, and then it changes shape, or appears to, as it goes back to being a new moon and completely invisible to us. What's happening? Well, it's just the bit of the moon that we can see that is reflecting the light of the sun, because the moon doesn't shine, it just reflects sunlight. There's no fire on the moon to generate that light. It's just reflecting sunlight back to us. So as it goes around the Earth, something very special is happening. If you're the sun, and I've got this light here shining on me, and here's the Earth, and this is the moon, and we have the moon going around. When we have a full moon, the sun, the Earth, and the moon are completely in line, and you can see essentially that full surface is completely illuminated and completely shining. But then when it goes around its orbit, the bit that's facing the sun, that's always still illuminated. But from your point of view, only about half of it or so is shining light back. And then by the time it gets to new moon, we have the sun, the moon, and the Earth. And now the bit that the sun is shining on and is reflecting light, well, it's the side away from the bit that we can see. So we can only see the bit in shadow, or in other words, the dark bit, the new moon, which is kind of hard to see because it's basically a shadow. And then as that moon goes around again, we begin to see the bit that's getting shined on by the sun, until finally we're back into the full moon and we can see the full face of the moon. So it's a great question. The moon doesn't change shape, but the bit that we can see is what's changing, and it's because it's going around us. I hope you then will ask a follow-up question, which is, well, if the moon is going around us, and it has to get that change in shape, why is it that, why can I always see the same bit of the moon? Why is the face of the moon that I see is always the bit, because although the bit of light is changing, it is always the same side that's facing you? Well, that's a very interesting question. I'll give you a hint. The moon is spinning. It's just spinning at the same speed as it goes around us, so it manages to always perfectly in sync and match up and allow the same face to look at us. It's called tidal locking. It's a little advanced, but I've got a sneaking suspicion that you'll be able to investigate that and study that and understand a little bit more about our favorite neighbor.
Daniel asks, how did the Earth form before dinosaurs walked the Earth?
How did the Earth form before dinosaurs walked on it? Well, it formed from that giant cloud of gas and dust, and that crunched together, and basically the sun was born in the middle, and then Jupiter formed after that, and then small bits smashed together to create bigger planets, protoplanets. Eventually you got something that was the size of the Earth or so, and we've had an interesting journey, and there's, oh gosh, I wish I could tell you about we think we got a collision from another object that smashed or tore a bit of us off that created the moon. The moon is actually a piece of the Earth that was ripped off during this collision. But I can't tell you any of that, although I just did. But what I can say is that the Earth was a very different place long before the dinosaurs. In fact, it was just the surface was just lava, molten lava, like you see coming out of volcanoes, incredibly hot. So no life could exist. And then slowly it cooled, and we began to see rain and water, and we began to get the oceans, and life itself began to form. And then through a process called evolution, simple life got more complex. And over time, we eventually ended up with more interesting types of life forms, starting with bugs and coming all the way like microbes to simple sea creatures. And then finally, we race forward to many billions of years later, and we find ourselves with the dinosaurs. And those dinosaurs walking around the Earth were then taken out by this comet, a giant event that smashed into Earth and caused we think a global firestorm, and that wiped out the dinosaurs, but little mouse-like creatures, little mammals, were then able to evolve and eventually one day become us. Now, we have this picture, but the issue is that the further back in time you try to look, and the dinosaurs, it seems forever ago, but we're talking like 60 million years for some of the things like a T-Rex, or maybe a couple of 100 million years. But the Earth's been around for maybe 4.5 billion years. And so in other words, there's so much time of the Earth before the dinosaurs, and the bit where we're at the tiniest little sliver at the end of the story so far. So when you try to look back in time, it's really difficult. So in other words, it's very difficult to answer your question exactly how they're formed, because every time, say, that big collision hit and ripped off the piece of us to form the moon, it destroyed all the evidence, because it all, essentially the heat of it, turned all the surface to lava again, so melting all the evidence away. So whenever we try to look for these clues as to our own history, we need to get very old rocks that are pristine, that haven't been changed or damaged, and still hold the secrets of those early times. That is why we're so lucky to be in Australia, because Australia has some of the oldest rocks in the entire world. Rocks that have been sitting for billions of years, waiting for someone with a keen eye for geology, perhaps like you, to investigate them and use them as a time capsule, as a little fossil, to understand what our Earth was like, how it was forming, how the Earth has changed in all of those many years, long, long before the dinosaurs walked this Earth. Thank you all so much for these incredible questions. Melissa, it has been a pleasure talking with you. Thank you for giving me the chance to meet some of your younger electorate and hear some of the fantastic ideas and questions that are coming out of Lindsay, out of Western Sydney. It's been a pleasure. Make sure you all keep looking up into the sky. We've had a meteor shower this week. There's other meteor showers coming in the months ahead. We have great events like the International Space Station flies overhead and you can see that. Get the ISS Spotter app and your phone will alert you and tell you when to go out and look, and you can see. And right now there are 3 astronauts above your head whizzing around every 90 minutes. So the world is a very exciting place. Even if you're stuck at home and you can only maybe look out a window or your backyard, you can still explore a lot.
Thank you to all the kids who submitted questions to Professor Duffy. I hope you enjoyed them, preparing those questions as much as I know that he enjoyed answering them for you. To hear more answers to your space and science questions, I have those available across on my YouTube channel.
Authorised by Melissa McIntosh, Liberal Party, Penrith.